Hello YouTube, my name is Tim Sander and today we're going to work a physics problem with kinematic equations for a hypothetical situation. Do not attempt this. We have some soldiers at the top of a 10-meter bridge and they want to time their jump so that they'll free fall and end up landing right here at the beginning of this canvas for a canvas-back truck driven by some bad guys. Our soldiers have a laser rangefinder. So they're ranging this truck. They know that it's moving at a constant velocity of 9 meters per second towards them, which is about 20 miles per hour. And they also know the position of the truck as far as how far away the truck is from them at any given point. So at what distance, delta x, should the soldiers jump if they want to land on their target, the canvas-back truck, right as it's passing underneath? Okay, so to solve this problem, the first thing we're going to want to figure out is how long it takes our soldiers to free fall the distance from the top of the bridge to the top of the truck. So we take our 10 meters, the height to the top of the bridge, we subtract 4 meters to the height to the canvas top, and we're left with a change in distance in the y direction of 6 meters. So how long does it take the soldiers to fall 6 meters? We're going to do a force diagram for the soldiers to figure that out. So the instant the soldiers jump, the only forces acting on them is going to be gravity. And Newton's second law tells us that the sum of forces acting on an object is equal to the mass of the object times the acceleration of the object. So the scalar components of that, you have negative gravity basically equals negative acceleration. So the acceleration of the soldier, if you simplify that, is equal to gravity basically, which is 9.8 meters per second squared. So we'll plug that into our kinematics equation for a change in position. We have the change in y, this distance here, is equal to the initial velocity of the soldiers multiplied by the time plus 1/2 the acceleration of the soldier multiplied by the time it takes to fall squared. And since the initial velocity of the soldiers, the second they jump, the instant they jump, is going to be 0, we can simplify and say that the change in y is equal to 1/2 the acceleration of the soldier multiplied by the change in time squared. So if we rewrite it in terms of time and plug in our variables, we find out that it takes the soldiers a time of 1.1 second to fall that 6 meter distance to where they would hit the top of that truck. Okay, now we want to find out the distance that the truck is going to travel the 1.1 seconds it takes for these soldiers to free fall from the top of the bridge to the top of the truck. So to do that, we're going to use the same kinematics equation we used before, but this time we're going to use the variables for the truck. And our truck only has movement in the x-axis. There's no y movement. So we have the change in position of our truck is equal to the initial velocity of our truck multiplied by the change in time that it takes soldiers to jump, plus 1/2 the acceleration of the truck multiplied by that same change of time squared. But since the truck's moving at a constant velocity, the acceleration of the truck is 0, so this whole factor is going to drop out. So we're left with the change of position of our truck is equal to the velocity of the truck multiplied by the time it takes the soldiers to jump. So plugging in our variables, we find that the soldiers should jump when the truck is 9.9 meters away, which is about 32 feet, and that should land them right on that canvas, and they can get the bad guys. Okay, since our soldiers were able to accurately calculate when they should jump, mission is accomplished. They're celebrating with a cold gnarly barley. Thank you for watching.